They have like a saying in Oxford, it's fortune and glory, and then everybody else says shame and disgrace.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. Your host today, it's me, Marissa Lowe, joined by John Pernay-Fisher.
Hello.
And Tom Harvey.
Hiya.
And our special guest this week is ice giant atmosphere detective Naomi Rowe Gurney.
Hiya.
How are you doing?
Yeah, good, thank you. Excited to be here.
Very good background, I see. Very on
Thank you. My bays.
Yeah. So you're in the third year of your PhD now?
Yes, just coming to the end of third year in September. It feels like it's like coming really, really quickly. So.
And you study planets right behind you there.
Mm-hmm. Yeah, Uranus and Neptune. I studied their atmospheres.
Wonderful. Would you like to tell us a bit of background on your project then?
Yeah, so my project it was made because I have a lot of data from the Spitzer Space Telescope, which is a telescope that's usually used for astronomy, so like looking deep into the universe or whatever, because it's in infrared. And they had this data back from 2007, and they needed to look at it a bit more closely and have a look at how the planets change as they rotate. So that's what I'm doing with my project. I'm using that Spitzer data to look at how specifically Uranus is rotating, and then I'm going to also look at Neptune towards the end of the project. And it's all in preparation for the James Webb Space Telescope, which is obviously hopefully getting launched next year. We'll see.
Yeah, that's really cool. So how much do we know about the atmospheres of Uranus and Neptune?
Very little, actually. There's not that much to read, which is good for me, I suppose, but it also means that a lot of the stuff that I'm finding out is stuff people don't know about, and a lot of the models that I'm using are based on other planets and other instruments, etc. So this is kind of all very groundbreaking stuff. So it's really exciting. It's just kind of unknown, so we don't know what we're looking at. So basically the end of my thesis is going to be, we still don't know what we're looking at, but we have all of this information to try and understand it later on when we understand more about the planets.
So what are the atmospheres of those planets like? Obviously they're just completely unimaginable compared to what we have on Earth. So, you know, what's their composition and yeah.
So they're kind of weird. They're really, really super cold. So Uranus actually has the coldest atmosphere in the solar system, and they're blue because they have a lot of methane in them. So that makes them different from the gas giants Saturn and Jupiter. They have a similar composition to Saturn and Jupiter, but the slightly smaller size and obviously the temperature difference. And then the high methane content means that we have very different processes going on. So like when methane gets lofted into the upper stratosphere, it gets broken down by the sun, and it creates all of these interesting photochemicals like acetylene and hydrocarbons that we can look at, and it can tell us more about how the atmosphere is circulating and what is happening deep below where we can't see, that kind of thing.
Well, because I guess these planets are quite far away, so how sort of well resolved are the spectra? Like how much sort of
well, that's the fun. I have 0 spatial resolution, so what I'm looking at is so Spitzer is used for exoplanets a lot. Where you literally look at a point of light and you take just that point of light and then you split it into its spectrum. So all you're seeing is one picture of the planet, and that is what I do for Uranus as well. Even though it's much, much closer than exoplanet, it's basically the same resolution, just slightly brighter spectrum. So we can get a little bit more detail spectrally, but spatially it's exactly the same.
Okay, yeah, that must be quite challenging then. So then, is it quite easy then using some of the spectra to then sort of go down into the atmosphere, and like how do you sort of then look at compositional changes like that? That sounds quite cool.
So we use a model called a optimal estimation retrieval model, and it's called Nemesis, and it was developed by Oxford. Yeah,
That's
they
an
have
excellent
crazy,
acronym. That's
crazy
brilliant.
Yeah.
names. I know it's a really contrived acronym. I can't remember what it stands for. The non. No, honestly, I can't remember. It's non-linear something
Oh, it's got to be
optimal
contrived.
something. Yeah, yeah. But it's named after the goddess of chaos or luck or something. I'm not sure. I'm terrible. They have like a saying in Oxford for when people use Nemesis. It's fortune and glory, and then everybody else says shame and disgrace.
Excellent banter.
I don't know why. Yeah, it must be an Oxford thing. But yeah, we use that to look at the spectrum, and then judging by where each like emission peak and absorption trough, where all of them are, and at each wavelength, we can then think, okay, so at this wavelength, we should be sensitive to this species and that chemical species, and this should be at this point, like this altitude in the atmosphere. So if you put all of these billions of lines together, then you can kind of figure out what's happening in the different temperature profiles and also in the temperature as well.
That's really cool. And then can you track it, I guess, as the seasons progress, or is that too complicated?
So the data that I have is only really for 2004 to 2007 for Uranus, and for Neptune it's 2004 to 2006, I think. And that means that we don't really have a seasonal change to look at for this data. Obviously, we can compare it to other data sets, but for Spitzer specifically, we're only looking at very short-term changes. So we're looking at the difference between one side of the planet compared to the other side of the planet as it's rotating.
Yeah, that's really
the
interesting.
days obviously are only like 17 hours, like 16, 17 hours for both planets. And then whereas the year for Uranus is 84 Earth years, and then for Neptune it's double that. So
wow. How often were the images taken? You said you had them over, 2 or 3 year time period, but were they taken every few weeks or months or?
So for the 2007 data, they're only taken over 3 days. So all we're looking at is literally a snapshot of the planet, and all we're looking at is one side of the planet at one time compared to the other side of the planet less than like 8 hours later. So
that's really cool. You can get all this information to then just off single profile. It's amazing. So
yeah, it's a great piece of instrumentation, the Spitzer Space Telescope. It's a lot more powerful than people know. Obviously it's used for really far away things, so we don't usually use it for things like this. So it's really exciting to be able to use it for.
Yeah. And you mentioned there wasn't much data then, so there's just not been many missions or telescopes that have been pointed at these outer bodies, or? Yeah,
unfortunately, Uranus and Neptune are incredibly neglected. They are, for some reason people don't want to know. I think it's because they're so far away. So Cassini has been to Saturn, and Juno and Juice and stuff are going to, or are at Jupiter or going to Jupiter, but it takes a lot more money. Obviously, money is the big thing to get, and time to get to the outer planets. Yeah. So that's why it's much harder to motivate people to want to look at Uranus and Neptune, because there's no goal. Like, why are we looking at them? We're not even visiting them. So we're kind of ramping up the hype now, trying to get people excited, because eventually we are going to go to these planets.
That's really cool. Did New Horizons go past these bodies on its way to Pluto, or?
That's a good question. I don't think it did. It's only had one visit and that was from Voyager 2.
And that's the pictures behind you, I guess.
Yes, yeah. These are the Voyager 2, like, this is what everybody thinks of when they think of these planets, because it's literally the only, like, really nice high def pictures we have. And this one, this one was taken in 1986, and this one was 1989. So, you know, the high definition, this was like the cutting edge tech of the time. So yeah, this is as good as it gets at the moment.
But yeah, that's cool. I guess you must be quite envious of all the pictures of like the moon, like the one John has behind him.
Yeah, true. But if they were closer, I probably wouldn't be as interested, you know, like I'm interested in these planets because we haven't been to them. And I want to know about them, but you know, these are the planets of my generation, because it's going to be I'm going to be the scientist that, you know, helps with getting to them. So exciting.
No, they're really cool. Like, I remember specifically those pictures of Neptune, just being fascinated by them as a child. I mean, so this is quite a basic question, I guess. So they're known as ice giants. So I guess, does that imply there's some sort of frozen surface at some depth?
So there's a lot of debate as to why they're called ice giants and whether they should even be called rock giants, because nobody actually knows what's inside them. We don't have enough information. Because to be able to know what's going on inside a planet, or even guess, you need to have an orbiter really to go around it and measure the gravitational field and stuff. So we haven't had that. So everything we're going on is just educated guesses. So what they think's inside is like a gas layer, and then below that, as things squeeze down and things get much denser and therefore hotter, you end up with a liquid layer. But this isn't like normal liquid, it's like a supercritical liquid, which is like not a liquid or a gas, it's like both of them. And then as you get hotter and hotter and denser, there's maybe this ice layer, and that ice layer is not a normal ice. Again, it's something called superionic ice, which they've actually managed to create in a lab now, so they know it's a real thing that happens at really high pressures and temperatures, and it's like this weird black hot ice, like water ice that is I can't even remember like what the definition of it is, but it's like black and hot and doesn't exist, like it's more like an ice plasma type thing. It's just so strange.
That's crazy. That's really cool.
So are there other data sets that you're kind of able to compare with, or is it comparing with, you know, data from other planets? And how does it work in that sense?
So we do compare to other planets. So a lot of the stuff that I'm using is using kind of the defaults for Cassini spheres when they're looking at Saturn. So we compare to that, but we also compare to ground-based studies, and also comparisons to the Voyager 2 data, which is some of the most reliable data that we have. So it did take some pictures like these ones, and it took some spectra as it went past and stuff like that. So we can look at some things and compare them, but obviously we don't have much to do that with.
That's awesome. That's some really famous data, isn't it?
Yeah. There's so many papers out there on it. Most of the papers for Uranus and Neptune include at least part of the Voyager 2 data.
Yeah, I think what I love about these old data sets as well is just how relevant they are still today as well. I think it's amazing that we can still gain new insights by looking at such old data.
Yeah, definitely. People are still like taking the raw data and reanalyzing them and finding out new things. So
yeah,
it's very important. And imagine what we could do when we have a mission there and get all of this new data. It's going to keep us fed for decades.
So you mentioned before that some of your work might contribute into what the James Webb Space Telescope will be eventually studying. Would you mind expanding a bit on that and saying how this might feed in?
Yeah, so the James Webb, I love the James Webb. For some reason, I just really enjoy the concept of it. So it's like this giant telescope that's, it's like 6.5 meters in diameter, the mirror in diameter. And hopefully it's getting launched in 2021.
And this is a Hubble replacement, basically.
Yes. So the scientific successor to the Hubble. So mostly the hype is about, like, around the James Webb is about it looking really deep into the universe because it's in this infrared wavelength instead of being invisible like Hubble is. So the more red you get into the infrared, the further you can look out, because you can look at redshift and stuff. I'm sure you guys know about all this stuff. Anyway, so what we can do with that is all of the Spitzer data is in this mid-infrared wavelength, and it's what gives us really good like compositional data for planetary atmospheres, and it means that we can look at the planetary atmospheres using the James Webb. And not a lot of people know that the James Webb is going to be used for solar system science. But it's going to be used from anywhere from Kuiper Belt objects and like small bodies, as well as the ice giants. It can even look at Jupiter, Saturn, and even Mars, as long as they're careful not to blind it.
Yeah, that's awesome.
That's so strange, though, that's going to be hopefully the next set of data that we'll be getting about the outer solar system.
Yeah, it's going to be really, really good data as well, hopefully. As long as it works properly, it will be. So at the moment, you either have to look at spatial resolution or spectral resolution. So all of my stuff is high spectral resolution because I have 0 spatial resolution. And then you see ground-based telescopes have a lot of spatial resolution. So they'll take a really beautiful picture, but it'll only be at one wavelength. So 0 spectral resolution, or maybe a couple of wavelengths. So James Webb is different because it will be able to look with both spectral and spatial resolution. So what you're doing is you're taking a picture, and then each pixel in that picture is going to be a spectra with multiple spectral points in it. And they call these pixels spaxels, which is fun.
That's going to generate a huge amount of data then, isn't it? I hope NASA have got some extra hard drives in.
Yeah, it's going to be huge. I can't even remember. Oh, they did say this in a meeting once, how big it was, and it was a crazy amount that they were sending back every second. So yeah, it's going to be great.
Yeah, because I guess James Webb is a bit further away, isn't it, than Hubble? So I suppose that's going to improve. Because does Hubble suffer from atmospheric effects and stuff, or is it still far away enough that actually it's still quite dark?
I'm not sure whether it does, but the problem with James Webb is that it's in the mid-infrared, which is where heat is. So any kind of heat radiation coming from any object is going to interfere with it sensing whatever it's looking at. So it has to go really, really far away from Earth to get away from Earth's heat. And then it has that massive shield on the back, which is the size of a tennis court, and then that is what shields it from the sun's rays to stop it from heating up from that. So,
and is this heat effect why people can't really do ground-based observations or meaningful ground-based observations of?
Exactly, it's Uranus, really, really incredibly difficult. I mean, they are getting better and better at ground-based. So you do get these beautiful pictures in mid-infrared now that, I mean, they're still very grainy, but you can make out the planet and you can even see the rings. And that was recently in the last 2 years that's been done. So my colleague actually was one of the ones that managed to observe the rings in the mid-infrared for the first time. So.
That's amazing, yeah.
So what made you decide that ice giants were going to be your point of passion for a PhD? Wonderfully alliterative.
So I didn't know I wanted to do ice giants until I saw the project, but I did know that I wanted to do atmospheres, planetary atmospheres, because I wanted to do meteorology. Oh, okay, let's start with my undergraduate was in astrophysics, physics with astrophysics at Leicester, but I hated astrophysics. By the end of it, I could not stand it. So I managed to do as few astrophysics courses as possible, and managed to do loads of planetary science courses. Realized I really enjoyed meteorology and like Earth weather and stuff and climate. But then went away for a long time and decided actually I do enjoy space, maybe not astrophysics, but I do like space. So I wanted to kind of combine the meteorology with the space. And that's when I realized that planetary atmospheres was a thing.
Yeah, that's awesome.
Yeah.
So were there many projects to do with that when you were seeking a project?
Yeah, quite a few. So probably I applied to about 5 or 6 places. A lot of places do Mars atmosphere. And I wasn't as interested in Mars because I like weird things, and Mars is like everybody does Mars, you know. I'm a hipster. I can't
Planetary
handle.
hipster.
Yeah, I can't handle when everybody else thinks something's cool.
Okay. Okay. Well, it's okay. I'm going to put you on the spot now. Which is your favorite out of the two, Uranus or Neptune?
I always get this question, and it's so hard because I love Neptune. I used to love Neptune. It was my favorite planet growing up. And I guess because of the color, like my hair is kind of sort of probably more Uranus colored now, but it started off Neptune colored. Yeah, so I really, really like Neptune, but actually all of my research recently has been Uranus. So I've kind of developed a soft spot for how weird it is. It's like the weirdest planet.
Because what's going on with its rotation again? It's weird, isn't it?
Yeah, it rotates on its side.
Right.
So that's why my project is so important. So the data in 2007 is at its equinox, which is the only time where you can view it side on and actually see it rotating. Otherwise, you're just looking at its pole.
Yeah, that's cool.
That's so strange to imagine, though.
Yeah.
Even when you're describing the structure of these things, it's just so different from anything we're used to.
It took me a solid month of the PhD to finally figure out why I could only look at it in 2007.
Yeah.
Were you there thinking, there's something wrong with this data?
Yeah, well, I was just like, why? I don't get it. And I was like, oh, it's on its side. Duh.
Yeah, so is there a big is there a big community of scientists looking at the ice giants then? Or, as we said, there's not that much data to go around, so are they as neglected as you said?
Yeah, it's getting better. So recently there was a meeting in London at the Royal Society for lots of ice giant scientists to go to discuss the future of ice giant science and hopefully try and figure out what we need and what we want from a mission. And that had over 300 people in attendance. There's a big picture on the ice giant Twitter. It's called at Icy Giants, I think is the Twitter handle. And that's super interesting. It was super interesting to be a part of. My supervisor was the one who organized the whole thing, so I got to be involved quite a lot, so it's nice.
Yeah, because I guess it's going to be important to put then exoplanets in their context as well. I mean, we have this class of planets here in the solar system, so it makes sense to try and get as much of them as we can if we're then going to think outside the solar system.
Yeah, I think that's one of the main tags that we use as ice giant scientists. Like, if you don't know the ice giants of our own solar system, then we definitely don't understand the ones that are out in the far reaches of the universe, you know. So using our solar system as our laboratory to kind of experiment on these ones to try and figure out what's going on is important.
Because are their formation then similar to Jupiter and Saturn, or are they fundamentally quite different in the way that they were built in the early solar system?
It's all still up in the air. Nobody really knows what the why Uranus and Neptune are so different from Saturn and Jupiter. There's theories going around that Uranus was created in like inner, like more like further towards us than we thought, and then it migrated outwards, and that's why it's on its side, and all sorts of things. So really, it's just educated guesses at this point.
Yeah.
Obviously, with scientists who study, say, the moon and Mars, a big approach to use is, let's take this principle from Earth and try and apply it to them. How much can you do that with, say, processes that happen in Earth's atmosphere for the outer planets?
Actually, quite a lot. The whole retrieval theory thing comes from like meteorology done on Earth. I mean, we have to use remote sensing slightly differently, but the whole process of remote sensing was created using satellites looking at Earth. So it's pretty it's pretty integral to kind of keep attached to the meteorology community. Otherwise you end up just reinventing the wheel all the time. And that does happen a lot in science, where people are kind of like, we have an idea, and then somebody's done it like 20 years ago. So it's important to try and stay current.
Yeah, that's amazing. I would never have thought there would have been, still such applicable links to Earth then. That's amazing.
Yeah, a lot of the books that I read are like Earth books about meteorology. So
yeah, that's brilliant. So I guess since all your data has already been collected, I suppose has lockdown affected any of your PhD then significantly, or?
I'm fortunate to be able to work from home because all of my stuff is data-based. That's I just make programs and analyze data online and stuff. So I don't really have to worry about being in a lab or anything like that. So nothing's really been affected. I was meant to go to NASA this summer to do a couple of weeks with some colleagues using the James Webb simulator. But obviously I can't do that anymore, which sucks.
Yeah.
So yeah, hopefully I'll get an opportunity at some point in the future to visit. I've been to NASA JPL before, but I've never been to NASA Goddard, which is where I was meant to go.
Yeah, that's a shame.
That you can reschedule it for then.
Hopefully we'll see. My PhD will be over by then. So sad. We're going to be doing it online though, so it's not all lost. It's just I don't get a cool trip to NASA Goddard. But,
yeah.
Boo-hoo, first world problems.
So you said before that you had a bit of a break between your undergrad and starting the PhD. What did you do at that time?
So weirdly, I left straight after university. So I got my MPhys in physics and astrophysics from Leicester. And then moved straight out to Shanghai, China for an internship in financial services.
Oh, wow.
And I was like, I'm going to be rich. And then I did it for about a month and I was like, nope, this is not for me. Hated it. But I loved China. It was an amazing place, especially Shanghai. It was a great city. So decided to stay, learn a bit of Chinese, and then eventually did a load of random jobs, like worked in a bar, and I was like a bouncer type person for a while, and did loads of really weird stuff. I was a DJ, so strange. And then I realized I still enjoyed physics, and so for the last 3 years I actually became a physics teacher, like got a small qualification in teaching, and became a physics teacher and tutor for the last 3 years, and the last 2 years I became a full-time teacher.
What made you think in the first place, I'm going to move out and get into finance? What was the draw there?
Literally, it was money. I used to be quite like financially motivated, and then after about a month, I realized I'm not financially motivated at all. And then decided against it. I am more motivated by knowledge, and once I'd learned everything that I needed to do the job, I was bored. So.
Yeah, because you wouldn't think that going to do a PhD. I wouldn't say that people who do a PhD are the most financially motivated.
No, exactly right. I've gone from one extreme straight to the other. Destined for a life of destitution now. So.
But then what made you want to get back into academia? Was there a moment, or was it just, I don't want to just be teaching this or flitting around from jobs anymore?
I think I always deep down wanted to do a PhD, but after 20 years of non-stop education, like going from nursery to primary school to secondary school to college, straight to university to do a 4-year course, I was done. I just needed that break. So it's kind of more like a gap year that got out of hand. And then I realized, okay, it's time to go back. After I got into the whole teaching thing, I realized that was just me like trying to justify not doing physics anymore. But then I realized, actually, no, I do want to do this. So
so how was it teaching in another country then?
yeah, it was really, really good. I don't think I have the patience or the motivation or the drive to be a teacher here. It's like the hardest job ever to even do it in a country like China. But over there, it was so much better because you get a lot of creative freedom to teach how you want. As long as the kids get the grades by the end, then you can do what you like. I mean, I redesigned the entire last 3 months of the curriculum to do more laboratory work and stuff, and that was really, really exciting. So it was a really, really fun job.
Yeah. Oh. Well, would you consider teaching again? Or I don't know what you're planning on doing after your PhD, but...
That is a good question. Honestly, I have no idea what I'm doing after this PhD. This was like I was like, I'm going to get a PhD, and then the plan stopped there. I would like to stay in the UK long term, but after the PhD, obviously there's a lot of opportunities to travel around with the postdocs that you do. So I would like to go somewhere for at least 2 to 3 years after this, and then probably move back to the UK to do whatever. But my partner also has itchy feet to get out. We actually met over in China, so we both have like the travel bug pretty bad. And now we've been in the UK in Leicester for another 3 years, and it'll be another year after this. So after that, we'll be like, okay, where are we going now? Yeah.
That probably leads quite nicely into the question we ask all of our guests while we're thinking about blue sky thinking and what else we could do. So yeah, if you could be doing something else completely different, either in academia or outside of it, what would you want to do?
Oh,
I'm so sorry I asked you this.
Anything. Oh my goodness. Okay, so I've always wanted to be a weather girl, like on the TV, like, you know, here in the Midlands, it's sunny, that kind of thing. Oh, I always wanted to be that. It's kind of what put me down the meteorology path, and then I realized actually I'm just a scientist. But yeah, that'd probably be what I'd want to do.
That's cool though. Yeah, that's a good answer.
Yeah.
I think with the background as well, it was like, so here's the weather out on Uranus today.
It's windy on Neptune today.
With light methane showers.
Yeah. The great dark spot is no longer there. Yeah.
Oh, well, this has been a really fun episode. Thank you so much for coming on.
That's all right. Thanks for having me. This has been a lot of fun.
Yeah. And all the best with the rest of your PhD. If you'd like any more Earth and planetary science content, all of our links will be in the episode description or on the thumbnail currently. But yeah, I think all that's left to say is thank you very much, Naomi. And
thank you.
Next week.
Bye.
Bye-bye.